Okay. Hello. Okay. So welcome to our tutorial for Gemmini, which is a platform that we've been building for full system, full stack DNN accelerator evaluation and exploration. We're going to talk about what Gemmini is and how it enables architects to make useful insights into the impact that different system components might have upon overall DNN performance. We'll go through a bunch of interactive sessions as well, where we'll create accelerators, simulate them, and inspect the profiling traces that might have come out of applications running on those accelerators. So feel free to ask questions at any time, either to me or to Simon, who's in the back, if you guys have any like tech-related issues. So I'll be the main speaker, but I couldn't. This definitely wouldn't have finished without help from other people like Simon or Seo or Dima will help me as well. Okay, and before we start, I'd like to quickly acknowledge and thank the DARPA RTML project, which is partially funding Gemmini and other related projects at our lab. Okay, so we have a 4-part program today. Before diving into those parts, we'll just quickly make sure everybody's set up on the AW instances that we spun up. Afterwards, we'll give a high-level overview of Gemmini, its motivation, its hardware architectural template, and how we can generate accelerators using it. Afterwards, we'll discuss Gemmini's programming model, and we'll show people how they can write code for Gemmini accelerators and run different applications on them. Then we'll look over some of the profiling and evaluation tools built into Gemmini, right? Which include, hardware counters that exist on physical taped out chips, as well as simulation counters, which exist only during testing and the infrastructure around them. And finally, we'll take a few minutes to give some, parting thoughts and some of our current efforts to expand Gemmini. And I think we'll be finished by 4 p.m. So after that, I'll just stay here till 5 p.m. in case anybody wants to ask questions or just chat about this or related projects or anything. But everyone's free to go after that. Or you're also free to go before that as well, of course. Okay. So first, let's get everybody set up. If you could go to this URL on your computers, this is a Google Doc that's got old instructions that we're going to run today. So some of the instructions are kind of long, so it's helpful if you can copy paste them. You'll also, if you search for part 0 setup, you'll also see a Google Sheet there. You can basically select an instance by entering your name next to it on the Google Sheet. So I'll leave this up for a second, and then I'll take an instance myself just so we can see how to do it together. And I forgot to mention this, but we'll release the slides and everything and the Docker as well. Okay, here. Let's look at the instructions ourselves. So if you see here, we have, you can just pick an instance. There's a lot of them, right? So you shouldn't, you can just take whichever one you want. Let's say I'll take this one, right? There's a permissions file for it, which you'll have to download. I've already downloaded that. And an IP address. So then after taking that instance, right, we can just SSHI and then Ubuntu at that. Right, and we have a Docker image. You should all have a Docker image already on it. Yeah. And you can log on to it using this command. So it's hard to copy paste like this. Okay. Then you can go to Chipyard, generators, Gemmini, but we'll have that path up later. Okay, and that's all. You're on our instance then. Is everybody good with that? Okay. Sorry. Okay. Yeah, so after logging into the AWS instance, log into the Docker image as well. You can do this in the Tmux as well. I think all the instances should have Tmux installed. And then just run the warm-up script that we're showing here on the slide. So this will take a few minutes to complete, but it should make everything else run faster afterwards. So let's run that together. So bash scripts, or sorry, tutorial warmup.sh. Okay, so just let that run for a few minutes. Okay, so now that we're all set up, we'll start with a high-level overview of what Gemmini is and why we created it. Okay, so it's not going to come as a surprise to any of you to hear that DNNs are becoming very popular, and people are trying to get them running on everything, right? From drones in the sky, to cars on the street, to phones in your pocket. Unfortunately, these DNNs tend to have very high computational requirements, which means that DNN accelerators have to be designed in order to run them in an efficient manner. So these DNN accelerators are also being put into everything, from small edge devices to power-hungry cars to huge cloud warehouses. However, designing new hardware accelerators is difficult, expensive, time-consuming, but every new physical environment imposes its own resource constraints, which means that many different types of accelerators are needed for the different environments and the different edge products that are just constantly being churned out by industry. And that means that accelerator generators are also exploding in popularity, right? So these generators allow architects to change maybe a few parameters in the configuration file or a few lines of a DSL and develop a whole new accelerator for a whole new environment at little extra cost. Now, existing generators each push forward the state of the art in different and important ways, but they don't always give architects all of the tools they need to evaluate the impact of the full system and the full stack on performance, and the ability to see how different components of the system and software stack might interact with the accelerator itself. Right, so when we are talking about the full system, what do we mean exactly and why is it important? So the system, as we use the term, encompasses everything from the SoC all the way up to the operating system running on the SoC. So the actual physical SoC can greatly reduce the maximum performance of the accelerator if its resources have not been well distributed among competing components. If we zoom in past the SoC itself, the memory hierarchy, not just of the accelerator's private scratchpad, but also of other CPUs and shared outer caches, can also impact overall performance, either in subtle ways, such as through cache coherence policies, or much more directly through miss rates and miss or hit latencies. The virtual address translation scheme, which includes the TLBs and the page table walkers, also impacts performance due to the possibility of page faults and TLB misses. Then at a higher level, there are the host CPUs themselves, which can actually have significant impact on total performance if you have any kernels in your DNN that cannot be efficiently offloaded to the accelerator, which is more likely to happen maybe in the field of machine learning, where new, unusual, and unexpected algorithms are often being developed for new networks. And finally, there's the operating system itself, running on the host CPU and supporting the DNN workloads that must be accelerated. So the operating system affects both the correctness and the performance of the DNN accelerator, because it forces it to reckon with new kinds of memory protection, as well as with interrupts, context switches, and other unexpected events that might harm total throughput if they have not been accounted for. And we ourselves actually dealt with a lot of bugs when moving into environments with operating systems and the overhead they have and the unexpected behavior they can cause. Okay, so above the system, we have a full programming and software stack that DNN accelerators need to be able to interact with while preserving performance and energy efficiency. So some DNN accelerators allow users to program their accelerators using only high-level APIs. such as TensorFlow or Onyx, which define the structure of the neural network, but do not necessarily define how it is to be offloaded. Others will allow programmers to call functions at a lower level, which offloads particular kernels, making it easier to integrate into new applications, but also harder for developers to program. And some allow users full control over the hardware's configuration and its low-level ISA, which allows dedicated developers to extract the maximum performance necessary, but which greatly increases the developer's cognitive burden. So where does Gemmini sit on the system and software stack? So Gemmini tries to allow users to evaluate this full space, as well as to tune the hardware accelerator itself. So some prior accelerator generators cover a subset of the space because they're usually trying to advance the state of the art in some particular corners of the space. But Gemmini's aim is to provide a superset of what they cover in order to provide architects with a comprehensive platform for their own design space exploration. So Gemmini's hardware template is relatively flexible, but it always follows the pattern shown in the diagram here. So first and foremost, there's the 2D spatial array at the heart of the accelerator, which performs matrix operations. The 2D array can be parameterized to support different data flows or different integer, floating, or custom data types. The array can also be configured to support different levels of connectivity so that both, let's say, CPU-like systolic arrays, oops, I think we missed an animation. Okay, we might be missing the animation. Yeah, so that both, TPU-like systolic arrays and more NVDLA-like parallel vector engines can be generated and compared for scalability and energy efficiency. Okay, so beyond that, Gemmini also adds support for non-matrix operations as well as, non-mathmal operations as well, with computational blocks for matrix additions in the accumulator, or for transposes, activation functions, max pooling, etc. Some of these computational blocks are optional, and they can be optimized out at elaboration time by the architect if you don't need those features. A new feature we've recently added is the normalization unit, which supports various normalization operations such as layer norm or variance of softmax. We added this parameter mainly to provide support for iBERT, which is an integer-only BERT variation, but we've tried to make it general enough to extend to other transformer variants as well, if people would like. And with this unit, we were able to improve our BERT performance 40x over what we previously reported in our earlier paper submission, mainly by avoiding offloading to the CPU some of these normalization operations. Right, so one caveat to note right now, if you want to take advantage of this unit, is that it only supports normalizations on the innermost dimension of a tensor, right? So batch norm still isn't supported, but we're working on it. Okay, so Gemmini also has a local scratchpad from which it reads data and to which it writes results. The scratchpad is parameterized to support different capacities, different baking strategies, different porting options. The local scratchpad reads and writes data to a global memory, which has its own cache and DRAM hierarchy, which can also be parameterized by the architect to have different levels, different DRAM controllers, etc. Gemmini gets instructions from a host CPU, which can be configured to be in order, out of order, low cost, high performance. To access the global memory, Gemmini accelerators are equipped with virtual address translation mechanisms, such as a local TLB, whose size and whose hierarchy can also be tuned. And Gemmini also includes reservation stations, which handle data and control dependencies between instructions, right? You can increase or decrease the size of this to change the number of instructions which can be in flight at any one time, although that's likely more of a second order performance effect. And we also have loop unrollers inside Gemmini. Users can write their own loops in software, but some loops are very common. And for those, Gemmini includes hardware loop unrollers, which have lower performance overhead and which can dynamically schedule instructions to achieve better performance than a lot of static schedules can achieve. Okay, and finally, the Gemmini generator allows users to put as many of these accelerators and has many of these CPUs on an SoC as they wish, hooked up to whichever global cache hierarchy they want. Okay, so before we go to the interactive activities, does anybody have questions about the template we've described so far? Yeah.
Is it bound to chip architecture? Because I know that one of the inference engines we used, they had significant issues with it running on different chipsets because the instruction sets were different.
Don't think we've tried going between chipsets. I mean,
Like if you're trying to running in like AMD versus Intel versus ARM.
oh, well, so this is RISC-V. Yeah, I should have mentioned that. So it assumes the RISC-V 64 format, like 64-bit format. I'm not sure how hard it would be to change. I think the basic programming model, I think it should be possible to extend it to like work with other host CPUs with other ISAs as well. But yeah, right now we're assuming 64-bit RISC-V, so two 64-bit RS1, RS2 vector, registers. Yeah. Okay. Any other questions? Okay. So if not, we can continue to the first interactive activity where we'll generate RTL and simulators for Gemmini accelerators, right? So first, in your AWS instance, in your Docker image, if you could go to the Gemmini directory and run this script just to set up some symbolic links. And then if you look within configs, you should see the 4 files in the configs subdirectory that we list on the slides. So we can run that ourselves. Paths, and then just checking configs. Yeah, let me zoom in a bit too. Yeah, okay. Okay. And then there we'll see configurations for different parts of the SoC, right? So firstly, you can open up Gemmini's default configuration. That's in Gemmini default configs. Let's open that first. And over there, you can see the default configuration we give, which is an 8-bit quantized configuration, mainly for CNNs, with a 16 by 16 systolic array, 256 kilobytes. You can change all of these here if you'd like. You can also see different options, right, for like which kinds of features it supports, whether it has certain optimizations, which can add area and power, but also improve performance. Options for the DMA, TLB, etc. You can also change the functionality of some things. So we allow, matrices to be scaled as they're being passed in. So by default, that's just the multiplication. But if you have some more complicated operation that you want to happen while matrices are being moved around, you can add that as well through the options. You'll have to implement them in Chisel, but you can do it in just a few lines of Chisel. Yeah, and over here, you'll also see, if you look, a new feature we recently added called the dummy config. So this is a configuration which is like the default configuration, but it replaces a lot of the operations and SRAMs with no ops. So the idea is it keeps the same cycle accurate performance, but doesn't have functional correctness. So this is just because some people need to build large configurations which might not fit on their available resources. So this can just make it run faster, as long as they're just trying to simulate performance. Okay, but we don't intend for most people to change that file, although they can. So for general users, we have a custom configs file as well, right? So that's configs. And over here, people can create their own custom configurations, right? You can create them from scratch, or you can just copy paste, or not copy. You can import some of the existing default configurations and just change individual parameters, for example. And then afterwards, we have several examples here, right, for people. But after you're done, you can creating your own config. You can just replace which one you want to build over here. right? You could make it any like vibrant configurator. Okay, and we'll play around with that. We also have CPU configs, same place. So we just have here like a collection of different host CPUs. We have, smaller in-order cores, larger in-order cores, more powerful, more expensive out-of-order cores, right? I think Boom Large is our out-of-order core, and I think maybe we could call a server class. If you want to have more fine-grained control over the CPUs, there's parameters for that as well within their respective repos within this Chipyard outer repo. But for most people, I think we just want to maybe switch between a few options. This is more convenient. Okay. Oops. Finally, you can see the config, which puts together the whole system, right? SoC configs. You can pick, for example, your L2 config options here. Its capacity, its latency, etc. You can decide how many CPUs you want. Each CPU also gets its own Gemmini accelerator. So this will also multiply the number of Gemmini accelerators you have. Yeah. Okay, so once you selected all your configuration options, right, Gemmini can produce multiple outputs, right? So first and foremost, it produces Verilog, right? Not very human readable, but functionally correct Verilog for this accelerator. It can also produce a functionally accurate simulator, which is useful for debugging, but it doesn't give accurate performance numbers, right? Its performance numbers are kind of garbage. It assumes most things just take one cycle to run, but it's fast. It'll also produce a Verilator simulator, or VCS if you have access to VCS, which is cycle accurate, a lot slower to run, but which can produce waveforms. As a wrapper around the Verilator simulator, we also allow people to run on a tool called MLSys, which is also cycle accurate, but unlike Verilator, has a more realistic DRAM, right? Like it uses real DRAM models, but will also be slower to run as a result of that. And finally, we don't go over this that much in this tutorial because there are other FireSim tutorials, but you can also directly take the output of these configurations and run them on a tool called FireSim, which is a platform for FPGA accelerated simulations on the AWS cloud, right? And that's pretty slow to build, right? Like maybe 6-8 hours, but it'll run a lot faster, obviously, like hundreds of megahertz or at least tens of megahertz. Oh, and one other thing to mention about FireSim is it can also run Linux. So if you want to run on real operating system, that's how you do it. On Verilator or MLSys, you can run on what we call a proxy kernel, right? Which is a very, very stripped down kernel. So that can give you some a virtual memory and some features like that. But if you want to run on full Linux with all of its functionality, you'll have to run on FireSim. Okay, so first, let's try to build the functional spike accelerator. All right, so we have a script for that. Just do a scripts build spike. This might take a few minutes to run. So what this does is it looks at your configuration options. It doesn't produce Verilog, but it produces an H file, right? Like a C++ header file that describes your accelerator so that can be fed into our functional simulator, and it knows how to represent it. These instances actually run a lot faster than we were expecting, so that's a good thing. On our own machines, this usually takes like maybe another minute or two to run. Okay, you can also build, Verilator or VCS simulations, right? Yeah.
We need to actually build all this stuff out.
Yeah.
Were you just building it on a laptop? So, for example, if I put it on like a C5.16 XLR or something, is this a point or what's it?
So you can build this on a laptop, but I usually build on our own labs, like Xeon servers. So this is an M5, M5.2x large. Like from what we can see, it's basically as fast as our seems to be a little bit slower than our servers, but not too much slower. So if you add this on like a C5, I think it would be fine. So Verilator compilation tends to be the slow thing, basically. But we've also added new options recently to parallelize that, so that should help. But if you have like a large thing, it could take maybe like 20 minutes or so to build the cycle accurate simulator on Verilator. It's faster with VCS.
Is it CPU or memory limited?
Sorry?
Is it memory limited, CPU limited, or both?
I don't know. I don't have the profile for the building. Yeah. There is work. This isn't my work, but there are people who are trying to make this run faster as well, like the whole Chisel flow run faster as well. Okay, so before you run build Verilator, you can also see some options, right? You can run a debug version, which will produce waveforms. If you don't add the debug option, you won't produce waveforms, but it might run a little faster. You can also parallelize it, right? So we added this recently. It's kind of like make, but you do have to put a space between the J right now. So maybe we'll clean that up later. But you can run, with more cores like 8 or 16 or whatever if you want. Okay, so let's start this. So first what it'll do is it'll generate the Verilog, and then it'll compile the Verilog into Verilator. Again, this takes a few minutes. Simon, do you remember how long this took on M5? Or we timed this 4 or 5 minutes? Okay, which is yeah. So it can take 4 or 5 minutes if it runs, but we don't have to wait for it. So we added a checkpoint where we just pre-compile this stuff for you, right? So you can just Control-C if you'd like, and then run this command. Tutorial checkpoint.sh build Verilator. Build Verilator. Okay. Cool. Again, you can build simulations with more accurate DRAM models as well. So that's what the build Midas script. So you get to choose between different DRAM controllers. First come, first serve, first come, first ready, first serve. You can also add an L3 cache if you want, right? So we have several options here. We'll just build with this one, for example. And then again, this can take a few minutes to run. So we've provided a checkpoint for this as well. So you can let it run to finish, or you can just run a tutorial checkpoint build Midas. And that'll just copy over pre-compiled binaries. Okay, so after you've built your hardware simulator, you have to compile the code that's actually going to run on it. So our software is in the software directory. So I'll leave this up for a second so people can go there. Software Gemmini tests. So this software is it's just C, right? There's nothing that special about it. We have a template file here in case people want to run their own like low-level code, right? They can look at the template. You just write ordinary C. We have a few defines like type depths for the data types that are running on the accelerator. We have low-level like C wrappers around the direct ISA instructions, but these are really low-level. And after you've written it, you can just run build.sh. That will build the actual binaries for those programs, right? So this takes a minute as well. There's a lot of things being compiled, so this will run faster if you have more CPUs for sure. But even on this machine, I think it finishes in just a few minutes. And once it completes, you'll be able to see the binaries, right? So it's basically just compiling RISC-V binaries, right? Like the exact same RISC-V binaries you could run on a normal CPU that you buy from Sci-Fi or wherever else, right? Except that if you call our own Gemmini commands, it'll also have the direct assembly ISA instructions for our commands. Okay, so it's built. You can look inside build, right? We build bare metal programs. So these run without any operating system available. They're statically linked. We also have binaries that will run on Linux, right? Dynamically linked. And we also have binaries which will run on proxy kernel, which is a much more stripped down version of Linux, which is basically just worth using if you can't afford FireSim, for example, but you want to run on something approximating Linux or a real operating system. So you can run the proxy kernel on Accelerator or VCS in like a reasonable amount of time, basically. Okay. Then if we go out 2 levels again, we can then like run the programs that we just compiled on our simulators, right? So we can see the options also, right? We can run with the proxy kernel, without, we'll run without. Oops. And then you just have to mention the binary that you want to run. So you can give a full absolute path to the binary, but you can also just give like the name of it and it'll know where to search for it. But if you have your binary in an unusual location, you can give the full path as well, right? We have, some handwritten models as well, like DNN models. Just for like example purposes, you can run them too. We have MobileNet, ResNet. We have iBert. Oops. Yeah. Oh, oops. This configuration is too small to run one of the larger layers of this network. Yeah, you can see a smaller transformer encoder layer. Okay. So Spike, it'll run fast, but it won't give you real performance numbers. It's just about functional correctness. So you can also run Verilator, right? You can run the template program, for example. I'll take just a minute. Yeah, so this is just loading data into Gemmini, doing a small matrix multiplication and checking that the result is correct. And you could run Midas as well. You don't have to do that right now. Okay. And if you want the actual Verilog, right, because you want to actually get the RTL instead of just the simulators, we save that as well in the generated source directory. And that the path there is kind of long, but you can just tab complete it really. So you can see whichever configuration you want. Like we built the custom Gemmini configuration, and you can see all the Verilog for it to your heart's content. You can search for Gemmini in here. You can search for the CPU. So it's all in here. Okay, so does that all make sense? Just the initial how do you actually run stuff on this? Oh, oh, I have a charger actually. Okay. Okay. So let's do a small interactive activity where we actually try to change the code, the source code a little bit, right? So we'll do a different type of configuration change. Instead of just picking different parameters, we'll actually add a new data type. Okay. So Gemmini comes, packaged with support for integers, signed integers, unsigned integers, different types of floats, right? We support arbitrary floats, basically, whatever exponent or significant width you want. But let's try adding a new complex data type, right? For complex numbers with real and imaginary components. So let's go over here and open this source file. And then search for a tutorial here. So we've already implemented most of the complex data type for you, right? You can also add your own data types as well using a type class that we added, right? So we made a type class just so people could add their own data types as well. But we've implemented most of it for this tutorial. But let's try to implement the addition operation for a complex number, right? So we have an example of the multiplication operation here. So self is the left operand, other is the right operand. So how would we do addition, right? And then we would just add the other one's real value, right? Oops. Yeah. And then our complex data type also wants to know the bit width of the output. So we can copy this from up above. Right, we can just pick the maximum. I mean, you can pick whatever you want here. The easy thing to do is to pick the maximum bit width of either the left or the right operands. Right, and then how would we do a MAC operation? So this is when you take M1 and M2, multiply them together, and add that to self. So we can use the operands that we already defined, right? So we could just do self, right, plus M1 times M2. So the answer is kind of in the comments. Okay, and there's other operators there as well, but we don't have to implement them for this tutorial. Yeah, and you can create whatever data type you want with that type class as long as its length is a power of 2. Okay, and yeah, and then let's open up our custom configs. And instead of building the baseline inference config, we can build a complex config instead. Right, and the complex config is just, see, we just copied the baseline inference config, but we just added a different data type, basically 16-bit complex numbers. Okay, does that make sense so far? Okay, and then again, just build var later. So scripts, build var later. So this will take a few minutes to run, so you can just Control-C if you want. Instead, run this checkpoint for build complex. Okay. And then we have to rebuild our tests because the data type changed, right? So again, go back to the software directory and rebuild the binaries because they're not using integers anymore. And then just wait for that for a minute. Sorry. Spilled complex. No problem. Okay. And then again, go out 2 levels. And we'll just simulate this on our cycle accurate simulator. Complex numbers. So we wrote a test here, which is almost the same as a template one. It takes an input matrix, a square input matrix of -I, right? And it just squares it with itself. And then the result should be -1. So let's just give it a minute to run. Let me zoom out a bit. So yeah, we can see that input matrix is a diagonal identity matrix, but it's -1I along the identity matrix. 16 by 16, so it might take a minute to print. Yeah. So some changes to the hardware actually don't need the binary to be rebuilt, but it's safest to just rebuild the binary every time because we haven't really made a list of the changes which will and won't change it. Basically, any change that's visible to the software, right? Like the data type, the dimensions of the accelerator are also visible to the software because it needs to know that to do some like tiling and stuff. So it's safest to rebuild the software every time. Sorry, running multiple like workloads at the same time? Yeah. Wait, sorry, are you talking about like within you create an accelerator and you want to run multiple workloads on the same accelerator at the same time? And you don't mean simulating multiple independent workloads in parallel. You mean, so we have infrastructure, and we'll talk about a little bit later for if you have like multiple matrix multiplications, for example, and you want to simulate like 10 different matrix multiplications on like different cores of your server at the same time. But if you instead mean that you've got like one hardware design and you want to simulate like multi-core workloads on it, then the easiest is if you run on FireSim, because then you can just use pthreads or C++'s threading library or the ordinary Linux multi-threading libraries, right? But if instead it's not about like running multi-core workloads, it's about running like single core workloads, but you want to run many of them at the same time, we have infrastructure for that. Yeah, so yeah, and we can see that the so we can see that the output, right, of the multiplication was -1, which is what we expect if we multiply -I with itself. Right. Okay. Yeah. That decision was already made before I joined this lab. So we use Chisel, right? We don't use Scala because it's Scala. We just want to use Chisel, which is just another RTL, right? So we believe it has some advantages over Verilog. Of course, there's lots of other RTLs as well, which have been developed, which try to build on top of Verilog. As for why Scala was chosen as the base language for Chisel, it's Scala, I think, makes functional programming kind of easy. And sometimes there are some hardware constructs that are simpler to describe with functional programming. But at the same time, it doesn't force you to use functional programming. It lets you use normal imperative types of programming instead, if you prefer. So one thing people ask a lot is whether Chisel will run on like Python or something. I think there was a intent to do that years ago. I don't know if anybody has pushed along that front recently, but like a different front end for it, basically. But it's also possible to program Chisel as if so that it looks very similar to Verilog, right? If that's what you're comfortable with, you can do that too. You don't have to take advantage of like all of Scala's functionality if you're not comfortable with it. But once you get used to it, it's hard to go back. Okay, that's session 1, the hardware stuff. Maybe let's break for 10 minutes. It's 1:51 until 2 p.m. If anybody just needs to drink water or walk around for a minute. Okay, so now that we've looked into Gemmini's hardware design, let's explore its programming stack a little bit. Okay, so we'll talk in this section about how Gemmini can be programmed at both low and high levels of abstraction. And we'll run through a few interactive activities where we run our workloads on Gemmini. So as we mentioned earlier, there are different levels at which people can program their accelerators. So Gemmini tries to expose 3 levels to the programmer based on their needs, which we call the high, the medium, and the low level programming stack levels. So at the high level, programmers can translate high-level DNN representations in the ONNX format automatically to Gemmini's ISA to run on Gemmini accelerators. At the medium level, programmers can use Gemmini's hand-tuned C library, which has implementations of different popular kernels like MACMOLs or convolutions or maxpools. And then finally, users can configure the accelerator directly at a very low level using direct ISA instructions. So this allows programmers to implement their own kernels if the ones that we give them are insufficient for their use cases or not optimized enough for their particular system configurations. So at the high level, like we mentioned, users can generate ONNX models and then run them on Gemmini, right? So ONNX is a file format or a data representation format for DNN models, which is supported by pretty much all major frameworks, right? So you can create models in PyTorch or TensorFlow and then port them to ONNX. And if you don't want to write your own models, there's a lot of ONNX models already available online for many different types of application domains, right? Oops. Sorry. Yeah. And then after you've compiled these ONNX models, you can use this tool called ONNX Runtime to run them directly on our own accelerator, right? So ONNX Runtime is not exactly a compiler, maybe more like an interpreter, which dynamically dispatches ONNX kernels to accelerators like Gemmini if they're available. If the accelerator has no implementation of that kernel, then it'll fall back onto the CPU in the worst case. Right, so through ONNX Runtime, we support both inference and training workloads, and we're running on our own fork, right? So the ONNX Runtime was created by Microsoft, but we forked it, and we've added new features to it, right? To automatically quantize models to int8, to do different types of op fusion, because a lot of accelerators require op fusion to get good performance, to change between different data formats, like where the channels are the outermost or the innermost dimension. And we've recently added support for some forms of model parallelism like tensor parallelism. This is a very recent feature. And some of these changes have been upstreamed back into upstream ONNX Runtime. And finally, after running with our tool, you'll also get a timing profile, which you can just plug into Google Chrome or another such tool in order to see in detail the exact runtime characteristics. At the mid-level, if you want to program directly in C or C++ instead, we have our own C library of kernels in this file call, in this header file. You just need to import a single header file. And another header file to describe your accelerator, but the tool will generate that for you. And then you can write your own C applications, which automatically call our handwritten implementations of convolutions, matrix multiplications, and that sort of operation. Our hand-tuned library will perform automatic loop tiling if you don't want to pick your own tiling factors. You can also pick your own tiling factors if you're using a tool like COSA or some mathematical model to find ideal mapping tiling factors. But if you don't, at runtime, it can use quick heuristics to pick the right tiling factors to try to maximize buffer usage. And yeah, so one caveat is we require the channels to be the innermost dimension, like TensorFlow. Some frameworks don't like that. They like the channels to be the outermost dimension, but like I mentioned last slide, Onyx runtime can also automatically perform those translations for you. Yeah, and we have implementations for lots of different things: mathmals, convolutions, matrix additions, mathmals and convolutions for both forward and backward passes, right? Input padding, input dilation, kernel dilation, all of that stuff. Okay, and at the low level, if you don't find the kernel that you want in our handwritten library, you can write your own kernels using the low-level ISA, right? But this is more uncommon. You might do this if you have very specific performance requirements, for example. So for that, we provide macros, right, in C, which are low-level macros in our header file around the direct ISA instructions. And we'll look at those a little bit. So for the low-level instructions, they're always expecting 64-bit RISC-V encoded instructions, right? For like this RISC-V, for the specification of these instructions, we use something called the ROC interface, which is an encoding format for custom accelerators. We're not the only one that uses it. Some other tools use this as well. For accelerators are meant to be attached to RISC-V processors as co-processors. So the Gemmini RISC-V ISA instructions are just interspersed between ordinary CPU instructions, right? So you write normal C code or assembly code, and you just plot these instructions in between, okay? And these instructions are then just passed directly to the accelerator whenever the CPU finds them in its decoding path. Okay. Yeah, so whenever the CPU encounters a ROC instruction, it sends it to its matching accelerator, and then it immediately continues CPU execution. So if you're using the low-level ISA, you will need to explicitly synchronize between the accelerator and the CPU with fence instructions. Oops. Oh, what did I do? Okay, yeah, so the CPU will basically send instructions with the corresponding RS1 and RS2 registers to the accelerator, and the accelerator just sends back either data directly to the L2 address or virtual translation, virtual address translation requests for the page table walkers, or just a single bit indicating whether the accelerator is busy or not so that it can be synchronized with fence instructions. Okay. So our instructions, our low-level instructions, are split between instructions which go within the load pipeline within a decoupled access execute pipeline architecture. So load instructions are those types of low-level instructions which send data directly from main memory to the scratchpad. once they're within the scratchpad, execute type instructions like mapmos or transposes or whatever will operate within data within the scratchpad and store the results back into the scratchpad or accumulator. And then store instructions will take the results in the scratchpad and send them back into main memory for where the CPU can access them if it needs to. Right? And each of these instructions can run independently within its own decoupled access execute pipeline. And Gemmini includes, reservation stations to do the checking for dependencies in between them so that you don't have to. Okay, yeah, so we looked at this file earlier, right? So if we just look at it again with what we know now, this is just a file using Gemmini's low-level programming interface, right? So it's mostly just C code, but interspersed with the C code are instructions to move data into Gemmini, configure the pipelines, and move results back out, and then just fence until the operation is complete, which freezes the CPU until the operation is. Okay. Does that flow make sense? Okay, so Gemmini's local scratchpad uses what we call row addressing, basically. So it's split. It's structured as a set of SRAMs, where each row of the SRAM is as wide as the systolic array is. So in order to be able to keep the systolic array or the spatial array completely filled with data every single cycle. Right. So if you're operating on data or matrices which have fewer columns in the systolic array, your scratchpad or accumulator might not be fully utilized because a lot of those rows, those columns in those rows might end up being just empty. Right. So the scratchpad and the accumulator can have different widths for their data types. For example, quantized data often requires the partial accumulations to be at a much higher bit width than the inputs. So you can have an accumulator which is 32-bit integers, for example, even while the inputs and outputs are just 8 bits. Okay, yeah. And then for instructions within the load pipeline, we have 3 different identical load instructions, which have the exact same semantics, but each has its own configuration registers. So this is just a convenience. If you have different strides or different configurations for your left matrix or your right matrix or your bias or different inputs, so that you can set configurations for each one independently and then load each one with separate instructions without having to change the configuration in between. Yeah, and each of these is generally a small granularity instruction, right? So you're supposed to tile them together into larger loops, and each one moves in submatrices, which are basically the same dimensions as the spatial array. And then you tile your larger matrix multiplications or comms or whatever with around these instructions that have the granularity of the spatial array. Okay. And then to configure these move-ins, you can pick different options like the stride, what scale to multiply them with as they're being moved into the scratchpad, etc. Yeah. Okay, the execute pipeline has 2 types of instructions, right? We have preload instructions, which load stationary data into the spatial array. So if you want to run weight stationary matrix multiplications, for example, the preload unit would store weights into the systolic array. If you want to do output stationary, they might store your bias into the systolic array, for example. Right, so you would have weights and you would put them within, preload them once so that they can remain stationary there. And then the compute instruction just feeds data into that spatial array with stationary units for matrix multiplications, right? So if you have a weight stationary array, you would feed inputs into it so that partial sums can come out. If you have an output stationary systolic array, you would just feed inputs and weights into it and accumulate the result within the spatial array itself. Okay, And you can choose different options like the data flow, if you made the data flow configurable at runtime, the activation functions to use, whether either of your matrices should be transposed, things of that nature. And then the store pipeline is similar to the load pipeline. You have a move out instruction, and it operates on data that has the same granularity as the same dimensions as the spatial array. But one difference is that the store pipeline also can perform other operations as data is being moved into main memory, right? So this is where normalization, activation functions, pooling, and things of that nature happen. So the idea is that you store your partial sums, accumulate them inside your accumulator, and then perform these kinds of activation functions as they're passing into main memory afterwards. Okay, and again, you get to pick, activation functions, scalar values to multiply your matrices by as they're moving into main memory, etc. Okay, and the last, I think, important thing to know if you want to understand Gemmini's low-level programming interface is the difference between what we call complex and primitive instructions. So what we've described up till now are, I guess, primitive instructions. They're kind of low granularity, right? They operate on smaller pieces of data, like 16 by 16 submatrices or 32 by 32 submatrices, things of that nature. And they control the accelerator at a very low level, right? And they also explicitly manage local and global memory. Our mid-level programming interface, like we mentioned earlier, is just a handwritten library where we compose these into loops for the users to use more conveniently. However, in order to make what we found while running these loops was that a lot of these loops are actually very similar and can just be hard-coded within hardware into a more fixed set of loops, right? So we include complex instructions, which are ISA unrolled loop instructions. So if we look at an example here, we might have like a nested set of loops, which use these low-level instructions one after another, right? And we might have several layers of loops which each add their own own software overhead, right? But we have these complex instructions which just fix the encoding for some of those loops into just a single instruction, right? And this reduces CPU instruction fetch and issue bandwidth requirements. And it also enables some other optimizations. For example, when the hardware is unrolling these loops, it can actually use dynamic scheduling rather than static scheduling because it knows exactly when dependencies become available or not available, right? And we found that in general, that can make your loops a lot faster, unless you want to do something fancy like software pipelining or very deep unrolling or whatnot. But unless you have a special tool or compiler to do that, it can be hard for people to do that themselves to see. Okay, so let's do another interactive activity where we try to just visualize and run an ONNX model on Gemmini. Maybe before we jump into this, does anybody have questions about the programming interface? Okay. So we have a ONNX model. We have a URL for it. You guys want to try downloading it. Oops. Leave this up for a second. Here, let me open it myself. Oh, it is. Yeah, it turns out that it is. Yeah, wow, this kind of stuff. Let's give this a minute, maybe. Okay, well, I have the model ready, maybe unsurprisingly. Should have it already. Has anybody been able to access it yet? Okay, here we go then. Okay, well, while we wait for that to download, you guys show you one with a model that's already on my computer. So you can download those Onyx models online from websites. You can generate them yourselves from PyTorch or whatever. Then you can just visualize them online, right? So you can go to this website, for example. Let's see if the website opens now. Okay, website seems to be opening. And you can load models directly into there. Right, so this is the model that you guys are going to download. And you can see all of the different operations in it. So this is an Onyx model that that's already run through our Onyx runtime tool, so it's already been quantized. Right, so you see the quantized operations. It's already gotten some op fusion happening with like ReLU and things of that sort. Okay, so after you, yeah. Yeah, oh no, it hasn't been run through Gemini, so it's just been quantized using our tool. So we'll run it on Gemini now, basically. Yeah, no problem. Okay, yeah, I guess we don't have to wait for you guys to see it yourselves. That's basically what it's going to look like if you see it, but you can go through all of the layers here if you want like help debugging or whatever. Afterwards, we can run it ourselves on our Docker images. So if you guys load the compilation of our Onyx flow, you can compile this yourselves as well. We have a command called build Onyx inference if you just want a single script to compile it, but that'll take a while to run. So we'll just do tutorial, checkpoint, build Onyx inference. That will just preload everything. Right, and then you can go to this path and you can run the model on like Spike, right, using our proxy kernel, for example. You could also run on there later, but it might take a while longer to do. So here, the paths are kind of long, but you guys can just copy paste them from here. So if we scroll down, we can CD here. And then we can see all of the different options we have in this Onyx runtime binary, right? It's just another RISC-V binary, basically. So you run it the same way you would any other. So you have different options for like batch sizes and optimization level and tracing and whatnot. We'll just run this model we had here. So this is trying to predict on a pre-trained model what this image is. Okay. Let's give it a minute to run. Might take a few minutes. So Onyx runtime uses some more complicated functions which don't exist in the bare metal programming stack, which is why we run it with the PK option with the proxy kernel. But that also makes it a little bit slower to simulate. Let's zoom in. Okay. So it's just going through every one of the 50 layers of less than 50 now. There's the residual additions, add convolutions. Just another minute. Yeah.
So, would we use another quantized, like any quantized model, or could you put with floating point?
So, you know, if you're built like a floating point accelerator, like we have options for that too,
Yeah.
in the custom configs, and you know, you can just run that directly. Otherwise, our like Onyx runtime fork will first pre-process the image to quantize it itself. So that's kind of like a more general solution. So it might not be as efficient as a quantization that you did by hand, for example. So for example, our tool does not quantize the very last classifier layer, because in a lot of networks, the final classifier layer can be a little bit tricky. You can do it by hand, but our automated tool doesn't do that. But yeah, if you want to be even faster, you can quantize it by hand. So
where you quantize and have a accelerator for students, but in practical sense, possibility and like fidelity to express something or whatever on your final layer.
right.
The both the conversation
Sorry, so if you have implementations of everything except the final layer,
yeah.
oh, so anything you don't have an implementation for will fall back onto the CPU,
Oh,
right?
what if what if you want to have a GPU hardware?
Yeah. Right. So Onyx runtime should support that. We haven't tested that yet because we haven't needed to, but that's kind of the whole point of it. So it should just work, where you can have multiple accelerators, and it just, for each op that it comes across, it kind of goes through them in order of priority and checks if it has an implementation for it. And if it doesn't, it falls back to the next accelerator. And if not, so in theory, we could have like, you know, NVIDIA Lay and Gemmini on the same chip and like pick between them. We haven't tested that yet, but it should work in theory. Yeah, no problem. Yeah, and as we can see, it predicted that our image was a Rottweiler or a Labrador retriever. Sorry, I don't know my dog, so I actually have no idea what breed this is. So yeah, at least it knew it was a dog. Okay. You can also run training. This is less efficient right now because we still have some operations like bash norm, which we don't have good accelerator implementations for. So those run on the CPU, and that can be a real drag on performance. But we do implement a lot of we implement both the forward and the backward like conv passes at least, right? So we can calculate the gradient of a convolution and the of a convolution layer or a fully connected layer, or a residual addition layer, etc. So you can run that as well. Simulating training takes a lot longer than simulating inference. So it wouldn't finish if we ran it anyway, even with maybe like a smaller batch size of just 10. So if you're curious, you can kind of just see what the log for that looks like. We've saved it here. So this is a log we got from running it on this Docker image. So you would see the same thing. And it would look similar in the beginning. Down. Oh, the right. So we would first in the forward pass just be calling convolutions and gem operations. Oops, I went back too far. But you would also be able to see the gradient calculations as well, right? Where you're doing fancier stuff like dilating the inputs or transposing them, etc. Okay, so I'm not sure if this will download faster. It's a much smaller file. Guys, I'll try downloading it to see how fast it is for you guys. Have it on my computer. Oh, this downloads pretty fast. So you will basically just get a JSON, right? You can save this yourself into any file that you want. I'll just save it in a text editor. So let's say my downloads, I'll put a wait, what was that? Oh. Okay. Sorry. I think I entered the wrong path. Okay. And then you can just in Chrome or any other tool for looking at these tracing files. Yes. Right, so just Chrome tracing, you can load these traces, and you can visualize them. You can see all of the different operations, whether they're running on a CPU or GPU, or sorry, or accelerator. This is yeah, this is a residual addition. You can see the other operations as well, right? In addition to seeing them visually, we also have scripts that can help summarize them for you on the command line. So we can run, let's say, the first one. Just going here. Oops. And then we can run different scripts to see, oh, oops. Oh, I miscopied the name. Right, so we can see summaries basically of how long each operation took and what percentage of the runtime it was running on the CPU or the accelerator or upon for which specific operation. Okay. Yeah, and let's do one last interactive activity for this session, where we'll try to mess around with the low-level ISA just a little bit. We won't write that much code. just modify it a little bit. So first we'll try to motivate why you might want to mess around with the low level ISA, right? So we'll try to make a specific shape of convolution more efficient on Gemini. Let's say we have a prepackaged implementation of conv for you, but it doesn't work very well with your specific conv. So I don't know, I'm guessing most of you, or at least a lot of you are familiar with convolutions. You have a bunch of filters, which are basically being dot producted with different areas of an input 3D image to produce an output 3D image, right? So Gemini flattens these images, right, to store within its own 2D SRAMs. And in the innermost dimension in its flattened format, it puts the input channels. Yeah, and then it breaks the convolution up into smaller matrix multiplications, basically, to compute the full convolution. Now, when the dimensions are nice and large, this works fine. You can keep your spatial array fully utilized, right? But when one of the dimensions, like let's say the innermost dimension is very small, then your spatial array may end up being very underutilized, because the dimensions which you're spatially unrolling are smaller than the actual size of your spatial array. Does that make sense? So does anybody know what people often do in this kind of situation? So there's different tricks, right? And other accelerators have done this kind of stuff. So one trick is you can do something almost like intercall and duplicate a small amount of the data so that you can spatially unroll along the product of two different dimensions at the same time, right? So instead of spatially enrolling just along the input channels, we can do it along the input channels and the kernel dimensions at the same time. So because Gemini's SRAMs are, 2D, and because we only allow each row of the SRAMs to be addressed rather than individual elements within the SRAM, this requires a little bit of data duplication. If you wanted to be more efficient in hardware design, maybe you could design something more like a window access, like a windowed access buffer. But we'll just do data duplication in this example, right? So then you get to utilize your spatial array a lot more. Does this make sense? Like in theory, everybody? Okay. Yeah. Very good.
Use with we have like some data here there's that use this like that spatial array. Yeah, because you're right. I think in order to have a more efficient computation,
Right.
You want to avoid like sparsity in this, right? So you do the information over.
Right.
Do you just like ignore it, right? The strategy say, oh, I get information, I get to do this on this computation.
Sorry.
You're moving over, do you like, can you keep some of that? Like we don't be, I guess maybe I don't know enough.
So you would have to recompute it, I think. But what you could do if you had more of like a specific buffer for windowed accesses, we didn't add this, but we could, but it was never required enough for our workloads. Is that instead of basically duplicating this like pixel across each row, you could have a buffer where you read out multiple rows and then remember like the last 3 elements that you read out, and then or something like that. Does that make sense? And then okay.
So you read out the last 3 or so. I guess the question is, would you do that to something out of your difficulty? I guess I'm not super familiar.
Yeah. No, that's a good question. Yeah, you could do that to reduce data duplication. So if we look at this figure above, we're accessing overlapping data basically, right? So if the overlapping data isn't along like the innermost dimension that we're spatially unrolling, then there's no data duplication necessary in Gemini. But just because of how it lays out memory, it doesn't make it completely flexible because it makes it more hardware efficient when it's more inflexible, basically. But the cost of that is that when you're overlapping data along the innermost dimension, sometimes you need a little bit of data duplication in order to avoid stalling the systolic array. So the idea is like you can only read out one row per site of this SRAM per cycle, right? So if this data is spread across multiple rows of the SRAM, you'll have to spend several cycles reading that out. So
You
yeah.
want to avoid that. Assume a lot longer.
Yeah, so that would kind of ruin actually the whole purpose. Like you're trying to make your systolic rate 3 times as fast, for example, or twice as fast in this example, because we were doubling the amount of like unrolling. So we're trying to increase utilization by like 2x. But if you make it so that every access takes 2x as long, it would not be worth it. Yeah. Yeah, no worries. And then there are other accelerators which do, if not exactly the same thing, a lot of accelerators struggle with the first layer of CNNs because later layers tend to have a lot of channels, but the first layer, because it's usually an RGB image, has just 3 or 4 channels. So this is a persistent problem for a lot of accelerators. So Gemini's mid-level library actually does include optimization specifically for this case, but in this interactive activity, we'll kind of imagine it didn't, right? And you're trying to write your own optimization. Okay, so let's look within the code base and open up our library in Gemini.h. And we'll look at an implementation of a tiled convolution tree for this tutorial. So this implementation is a lot slower than actual implementations we have because we were trying to make it simpler, right? So let's go out a few levels. Oops. It's hard to type like this. Okay, so we'll do this in 3 steps, right? So firstly, in our implementation of this convolution, we first move in all the input data, then we do mathmals on it, and then we move the result out, right? So kind of simple. Oops. Over here, K represents the number of columns that we're moving into the scratchpad, right? So we're moving in 1 column into the scratchpad at a time because we're assuming we have inputs with just like 1 dimension, like one input channel, for example. But let's say we want to move in 3 input columns instead, right? What would we multiply K with in that case? Yeah, so 3, right? So the idea is, yeah, we're just moving in more data into the scratchpad in every movement. Okay, then in our convolution operation, we're doing like a deeply nested for loop, a 7 nested for loop, I guess, because convolutions are 7 nested for loops. And we are trying to iterate over 3 kernel or input columns at the same time, right? Instead of just 1. So in that case, instead of iterating 1 by 1, we would iterate 3 kernel columns at a time. Right. And then the last thing, K represents the shared dimension here of a small matrix multiplication. So we're tripling the size of this as well, right? So we would just multiply this by. So that'll make sense. So we're doing mathmals, but just 3 times as fast, both during move-ins and matrix multiplications. Okay. And then let's go out 2 levels, build the baseline configuration. And then build a spike image for it. That's just like a minute or two. And then we'll run it on spike just to verify functionally that we didn't break anything with our changes, right? Because when you're messing around with the low level IC, it's very easy to make mistakes. Okay. Let's go and build the tests now, the software. Right. Let's wait a minute for that as well. You can ignore these errors. When you're running on Docker, sometimes they appear, but they're not real. It didn't actually error out. The only reason this takes a while is because of the handwritten DNN models. And the only reason they take a while is because they have very large weights, like 50 megabytes of weights for SN50, for example. And it's just like discreting, it just has to read all of that into the binary. Okay. Then let's just run the first layer, right? Their optimization. So this is a conv with very few input channels in the first layer, but 3 kernel columns, and it works. If it failed, it would have told us that the matrix wasn't what it's needed to be. So again, with Spike, you won't get real performance numbers, but if you ran these on Accelerator, you would see that our optimized conv for this case ran like 52% faster. Right? Didn't run 3x faster because we still have other overheads, like from the loop overheads and stuff. And our actual implementation will be faster than both of these. But hopefully this gives you a little bit of taste of messing around with the code in the Gemmini.h file itself, if you want to. Okay, that's the end of the programming session. We just have one more, which is just about profiling tools, evaluation tools in Gemmini. Again, we take maybe a 10-minute break and meet at 3 p.m. Then we can wrap up. Okay, and we're at the final section of the tutorial. So this is where we talk about how to profile Gemmini and how to use the evaluation profiling tools in it. Okay, so we'll talk about the different types of Gemmini counters, whether they're hardware SoC counters or whether they're counters that exist only in simulation. And we'll go through a few interactive activities. Okay, so firstly, Gemmini has counters that exist on the SoC, right? So these are counters that will exist on a taped out chip. So they're useful for profiling actual chips, but they may also affect, your area or power, probably not your performance. And then we also have counters that exist only in simulation, right? So these exist during FireSim simulations, to be specific, and they don't affect the performance or area or power of your chip. So SoC counters are configurable. The architect or the user can decide how many to add at elaboration time. You can have none of them if you want to save area. The user can read them instantaneously at any moment, or snapshot them all at once so that they can be read one by one in case they're changing faster than you can read them. So some of these counters are monotonic, right? Things like TLB hits or misses, they always go up. You can reset them, but they won't go down other than when you reset them. And others are non-monotonic, like the exact reservation station utilization, how many in-flight instructions you have, they may change from moment to moment. So those might be more useful to snapshot. So you can have as many counters as you want, but they all begin disabled, which means that they're not counting anything. Afterwards, the programmer decides which signal, which is represented with just a counter code, that he wants them to count, right? So this can be things like TLB hits, average DMA latency, stuff of that nature. And once you enable a disabled counter, it gets connected to whichever signal you want it to count, and it just it will represent that signal. The simulation counters, like we mentioned, only exist in FireSim simulations. So they're accessible through logs. Some of these, again, represent monotonic counters, right, which just always go up, based upon a Boolean signal. Others represent non-monotonic counters, right, which can go up or down. And then we also have some memory stats, which FireSim can generate for us for accesses to outer memory, to the L3 cache, or to the DRAM itself, right? And just to be clear, if you want to use the FireSim simulation counters, be sure to set this parameter, use FireSim simulation counters to true in your custom configuration. Yeah, so we have, both SOC and simulation counters, like I mentioned. We have them for signals like TLB miss or hit rates, the latency of different Gemmini DMA requests, bandwidth, reservation station stats, the estimated overlap between instructions in your execute, your load, or your store pipelines, because ideally you want that overlap to be as high as possible, or stats to try to tell you why your DMA might be blocked installing, right? But we're happy to add more counters if anybody needs more counters, so you guys can just let us know and we'll be happy to add them. It's not difficult for us to do. Okay, let's do a few quick interactive activities. So firstly, let's look at some of the simulation logs just to become a little more familiar with them. So these would come from running FireSim. Running FireSim would take definitely too long for this tutorial. So we've saved the outputs in our tutorial repo, and we can kind of look at them. So we can look at one of the log files for the monotonic counters. In FireSim will be called auto counter file. We just call the counter.log to shorten the name. This is from the output of a ResNet 50 inference. And let me zoom out a little bit. You can see that every however many cycles, you can choose the frequency. It will just tell you how many times a certain signal has been asserted, right? And towards the end, some of these signals have been asserted, let's say, millions of times. Others maybe not at all. Okay. FireSim we also have FireSim counters that are already packaged inside Gemmini for you. You don't have to add them for non-monotonic counters, right? So you can open up printf-log to see that one. Okay. And tutorial. Yeah, you can see in the instantaneous values, right? Or counters which may increment by more than one at a time, like the total number of bytes sent through the DMA or received through the DMA. And you can see that they may be in the millions by then. Okay. And finally, we can see various statistics for the outer memory units. Tutorial. Sorry, this is getting in the way. Packaged inside a CSV file for us. Okay, so you can read this with pandas or anything, and you can see the number of accesses that were made to the outer DRAM banks, the number of times they returned values, total writes, reads, that standing writes, etc. Okay. Okay, so maybe let's look at how we could look at those logs to try to estimate the impact of one specific component, like the TLB, on the performance of the overall accelerator, right? So first we'll motivate this by talking about a case study we did. So we were kind of interested in how virtual memory, something like virtual memory, could affect DNN performance, right? So with Gemmini, you can construct two-level TLB hierarchies where the CPU and the accelerator can each have their own private TLBs, and the L2 can have its greater shared TLB, which everything else falls back, right? Now the virtual memory statistics for DNN workloads can sometimes be pretty different, maybe from like workloads like spec or CPU workloads that you may be more familiar with. For ResNet 50, for example, we see that the TLB hit or miss rate can change a lot throughout the lifetime of a single inference, and can also be quite high, like as high as 30% or so, which may be higher than you're used to in some CPU workloads. And this is mainly because DNN workloads are oftentimes very tiled, right? So you're oftentimes going down just a few rows can push you it can push you into a whole new page, basically, if you're working on strided data. And in fact, we found that the TLB can affect performance noticeably, right, like up to 15% or so. And the size of the smaller private TLB was much more impactful for overall performance than the size of the much larger shared TLB, even though the shared TLB could have hundreds or even like 1,000 or so elements, and the private TLB would have only just a dozen and still be more impactful for overall performance. And we were also able to experiment with simple optimizations like adding a single entry L0 TLB to filter out consecutive requests to the same TLB page, and found that added, very cheap but low cost but noticeable performance improvements. So we can look basically in the logs that we looked at earlier, TLB, local for. So we can look for each of these different configurations within the FireSim logs, and we can search for TLB wait cycles. And this is a counter within our tool that will tell you exactly how long the DMA was spent stalling and just doing nothing, only because of the TLB, right? There was nothing else that it was working on. It would have been ready to go immediately if not for the TLB. And you can look at it at the very end, right? So I'm not looking at to remember the exact numbers, but as we look at these different configurations, we can notice patterns about how those values are changing or increasing or decreasing. Right, and what we find is that, again, as we're moving along the diagonal of these figures, the total amount of time spent waiting for the TLB goes down very noticeably, right? But much less so once you've already gotten 8 elements in your private TLB. Okay, so this, even if the total amount of time spent waiting for the TLB goes down, by like 3x or whatever, that doesn't necessarily mean your accelerator is 3x as fast, because there's other bottlenecks as well. But with these kinds of logs and with these kinds of counters, it makes it easier to try to filter out each bottleneck as it emerges. Okay, so those are the simulation counters. Let's do a interactive activity where you play around with the SOC counters, right, that are in the hardware itself to try to investigate maybe higher level bottlenecks in an application. So we will look into how different layer shapes affect DNN performance in single and dual core cases. So the motivating example here is sometimes you'll want to have multiple Geminis within an accelerator, right? And each Gemini might have its own local private scratch pads and SRAMs, and might have shared outer memory that they're falling back on, right? And we want to know exactly how to partition memory within the system based upon the characteristics of the DNNs themselves. So we published a case study about this in our original paper at DAC. You guys can read it online. But the summary is that in the single core case, we found that making the private scratch pads larger was much more helpful for performance than adding the same amount of SRAM capacity to the shared outer caches, mainly because the convolutions had a lot of data reuse opportunity, and they were really able to take advantage of the private scratch pads. However, in the dual core case, the shared L2 was a lot more effective for overall performance improvement than increasing the size of the scratch pad. And that was despite the fact that convolution still benefited from larger scratch pads. And the main reason why we found was because of the residual additions. So residual additions have low arithmetic intensity. And in the dual core case, they would sometimes compete for space on the L2. Right? Residual additions will produce an output and then use them maybe several layers later. So if you have a large enough L2, it might still be resident there, but if you have multiple applications, each with their own memory spaces, they will be competing over that, and getting that kicked out can force very expensive reads to outer DRAM. Okay, so let's do a small exercise where we try to add our own hardware counters, right, to the Gemini application to try to figure out the cost and the overhead of these residual addition layers, right? So we will open up this file, ImageNet profile ResNet tutorial. This is just a sliver of ResNet 50, basically. And we'll add code here to try to, around the residual addition layer, to try to figure out, both how many bytes were read in total and how many cycles were spent stalling solely because we were waiting for accesses to the L2 cache, right? Like where the accelerator could have continued doing useful work if not for this. Okay. Yeah, sorry. Okay, so we have 8 counters in this build, right? So we can choose whichever 2 counters we want to read whichever of these signals we want, right? Like we could do 0 and 1. These are the 2 obvious choices. But we could also do 0 and 3, or, 4 and 3, whatever. We can tie whichever signal we want, counter on to whichever signal. Let's do 0 and 3, for example. Afterwards, we can look within this file, Gemini counter.h, for the actual counter values, right? The codes for each type of signal that we're counting. If we search for bytes, we can find the RDMA bytes received. So this would be the number of the number of bytes that were received by the read DMA. So this is the total number of bytes counted. You can do that again to search for stall signals. This is I don't have my vimRC here. Sorry, give me a second. Cycle is this. Okay, so we can see the amount of time that the load DMA is basically stalling and waiting and doing nothing useful. Okay. And then afterwards, if we want to read these counters after having run a residual addition layer, then we just remember which numbers we set them to, like 0 and 3. And then we just print those values out as just unsigned integers. Okay, so we can compile this. Just give that a minute. Okay. And then we can run this on our functional simulator Spike just to check. Let's check that we didn't break something or cause a segmentation fault or whatnot. So the actual performance SOC counter values on Spike will not be accurate because this is just for functional correctness, really. You'd have to run it on Verilator. That would take a few minutes. So we've already run it on Verilator for you guys. But you would do it with the same command. Just run Verilator instead of run Spike. And then, you would be able to see that in the single core case, when running on Verilator, or FireSim, I suppose, the residual addition cycles become a lot more expensive in the dual core case, and our bandwidth for the residual additions drops a lot more substantially in the dual core case. And we spend a lot more cycles just stalling and waiting. Yeah, so we spend almost 80% more cycles just stalling for the read DMA just during the residual additions themselves in the dual core case. Okay, we have one final interactive activity. So this is also a newer feature to Gemmini. We've recently added the ability to simulate many workloads in parallel. This is added by one of our undergrads, Divija, who's actually here today. So this is basically motivated for use cases where, for whatever reason, you can't run very large workloads on FireSim or some kind of FPGA accelerated platform, right? And if you want to run a very large workload like ResNet 50, for example, on Verilator or VCS, it's going to be very slow. It can take like several days to run. But an alternative, instead of running, alternative to running, every layer of ResNet 50 sequentially could be to just run every single layer in parallel. So that won't give you all of the, subtle cache maybe effects of running sequentially, but it can give you a closer approximation of the overall performance. Right. Okay, so we have infrastructure to do that for you. Of course, you could run each layer individually yourself in your own script, but we've also built scripts, like convenience scripts, to let people do that easier. We will go to this directory, Gemmini data collection. And all of the instructions I'm going to describe now are in the README over here. But we will first create a template for the test that we want to run. So if you guys remember, earlier we made the first layer more efficient, right? So we might want to see across a more diverse set of workloads, across a more diverse set of shapes, how much better does this optimization help, right? And we can copy that into templates. Afterwards, we open up the new template that we added. And then any parameter that we want to change, we replace it with whatever parameter name we want, but surrounded by these ampersands, right? So we can replace any. It's kind of like a preprocessor, like the C preprocessor. We can replace any text we want, and we can name it whatever we want. Just to make things simpler, we'll just go like batch size and output chunks, for example. Okay. Afterwards, we specify which parameter instantiations of these parameters we want to run simulate in parallel. So we have this tests.py folder. We already have a few test examples here. For example, if you wanted to run several matrix multiplications and convolutions in parallel as examples, we can comment them out right now. So we don't want to run them. And we can instead add tests for this new conf first layer template that we added. Right, so we have we can just copy paste from here. Oops. Okay, so we specify the parameters that we want to change, right? We specify the values we want them to take. We specify the name of the template, and then we specify the name of the folder where the results of this will be found, right? So we can name that anything. It doesn't have to be conf first layer 1.4. It could be just my test 1 or whatever. We're just naming it this to make it easier to know exactly what you're on. Okay. And then we just run this script. We tell it which hardware configuration you want to run on, right? So this is whichever hardware configuration is in the custom configs file. We'll just run them on the baseline inference configuration. And we specify whether we want this to run on VCS or Verilator or MLSys. So baseline inference. And then what that'll do is it will, every one of the things that we specify the tests, it will build them and run them all simultaneously on separate cores of your CPU. Okay, so this will take a while to build and run. So we can just Control C this right now. And go out a few levels. And load tutorial for this, load the checkpoint for this instead. Yeah, and then we get to see the outputs, right? So we can see, for example, the cycle counts for each of those tests. Paths can be kind of long, but they're in the file. So like conf first layer, whichever configuration you had. We can see that this one took 233,000 cycles. We can see that a smaller configuration, fewer cycles, a lot fewer cycles, right? We can also see tiling factors. So if you're using any like Gemini local, like Gemini's mid-level library commands within Gemini.h, they can also print the exact tiling factors that they chose for you heuristically if you didn't pick your own tiling factors. So we also have paths for them here. Tiling factors for whichever one we want. So we can see how that shows the batch tiling dimension, output tiling dimension, etc. Okay, and then running this script tends to generate a bunch of intermediate files. You don't want them polluting your directory. The script will also automatically generate a clean script for you, so you can just erase all of those intermediate files. Okay. Okay, so any questions about the profiling or validation? Okay, so just some parting thoughts then before we wrap up. So in summary, Gemmini is a full system, full stack DNN accelerator evaluation platform, right? And our aim is to allow people to tune different components of the full SoC and see how they interact together, and also experiment with different levels of the programming stack, maybe for different use cases. So some future plans. Gemmini right now is hyper focused on dense workloads mainly. So we have dense DNNs and dense transformers. I think we've run RNNs on this as well before, but they were always dense, right? The design space for sparse accelerators is a lot broader than for dense accelerators, right? Because it's not just the accelerator itself which changes; it's the sparse data format, it's the load balancing techniques, etc. So we would like to extend it to this larger domain. We're working on that right now. We're hoping to submit a paper about it within not too much time. So we'll see. Maybe by next year there will be a published paper, another presentation or something about that. I'm most happy to talk about that if people want to. We are also just work on engineering improvements, continuing, right? The training training performance is still limited, even though it's supported, mainly because of the batch norms, and just continuing power and area improvements as well, right? We have people who are making different components smaller and more efficient. Okay, and yeah, thank you guys for attending. So a lot of people helped with this tutorial, helped put it together. Yeah, so that's the end. If anybody has questions, I'd be thank you. So if anybody has questions, I'm happy to talk about this project or about anything else that you guys are interested in. And I'll pause the recording.